Okay, hi everyone. Welcome to this week's ArchAgenda debates. This event is being recorded and live streamed on ArchAgenda's YouTube channel. My name is Daniela Girdovich, and I'm the curator of the ArchAgenda debate series at the Chicago Architecture Biennial. ArchAgenda is a program partner of the Chicago Architecture Biennial. And this year's series kicked off with a two-day symposium titled ArchAgenda Debates, Cyber Urban Incubators in the Blockchain Metaverse, followed by a keynote lecture by Patrick Schumacher titled Design Drivers in the Metaverse. And last week we had Shege Bushan and Alicia Nachmad presenting on realizing cyber-physical communities. You can find these complete videos on the ArchAgenda YouTube channel. Today, it's a great pleasure and honor to welcome leaders from across SOM's interdisciplinary global practice. And this event continues the series of free online events that will occur every Saturday from now until December 4th, starting at 11 a.m. Central Time. These are the events that are coming up. On November 20th, next week, we have Theodore Spyropoulos giving a keynote. He's the director of AADRL and principle of minimum forms. On November 27th, we have architect Jimenez Lai, who's the founder of Bureau Spectacular, and Stephen M. Johnson, a former R&D product developer and urban planner. And then on December 4th, we have Design Morphine talking about their practice and their new online master's program in advanced computation. If you're interested in these events, please visit the Chicago Architecture Biennial website to register. They're all free. The theme of this year's biennial is the available city. And I just want to tell you a little bit about the structure of this particular series. So ArchAgenda debates aim to spark lively and candid exchange on 21st century architectural and societal paradigm shifts, fueled by globally distributed cloud communities, emerging economies, new governance models, novel design agendas, and innovative technologies that transform social synergies, entrepreneurial opportunities, and the process of building cities. The fluidity, mobility, and dynamism of 21st century network society is transforming the way we design cities. Current societal paradigm shifts are marked by an intensification of systems of communication, complexity, coevolution, responsiveness, and freedom. Urban design innovation is accelerated by the convergence of natural and artificial intelligence, the emergence of distributed peer-to-peer computational networks such as blockchain, advancements in telecommunications, the explosion in real-time decision systems using big data and AI, the movement towards knowledge economies anchored by research and development. And in this context, we can view the world as a laboratory. Broadly, this series of events aims to form a gradient of topics in architecture, urbanism, and design, ranging from virtual reality to mixed reality to fully functional cyber-physical and physical communities. With this framework in mind, this particular event was authored by SOM and organized in partnership with ArchAgenda and the Chicago Architecture Biennial. On a personal note, it is really a great pleasure to have been part of SOM's Chicago office for a number of years, working on some amazing large mixed-use projects featuring some of the world's most innovative towers. So this event is very special to me, and I'm very grateful for the presenters who are here today. I'm going to read you SOM's own description of this event. We're welcoming leaders from SOM's interdisciplinary global practice, and they will deliver a series of presentations followed by a panel discussion and Q&A. Presentations will range from strategies and solutions on post-pandemic workplace to advancements in fabrication and design technology that have the potential to disrupt the construction industry, and climate change responsive design solutions that emphasize planetary health. SOM is a laboratory that is constantly exploring new ways of practicing design. For decades, the firm has invested in research that has transformed the architecture, engineering, and construction industry, from developing some of the earliest collaborative CAD platforms to devising engineering solutions for the world's tallest building. Every year, design and research teams at SOM generate new ideas that challenge how they will collaborate and build in the future. These ideas have a proven history for becoming industry standard practices worldwide. Programming will explore SOM's design research of the past, present, and future. So I'm going to read you who's presenting today and the subject that they're talking about. So our first presentation is going to be about SOM's history of innovation, and that will be delivered by Neil Katz, who's an associate principal. The second presentation is on spatial laminated timber, or SPLAM, and that's going to be delivered by Benton Johnson, who is a principal at SOM, and Kyle Vances, who is an associate. Next, we will have a presentation titled Moon Village, which will be delivered by Daniel Inocente, who is a senior digital design architect. The following presentation is going to be 3D printed structural components by Georgie Petrov, who's a senior associate principal. Then we're going to have another presentation titled Microbial for Life, Human and Nature by Leong, who's the principal at SOM. And then a presentation titled Wildfires, which will be delivered by Justin Leong, who's an associate, and Daniel Zweig, who is a senior architect. And finally, we're going to end with a presentation titled Urban Development Prediction, delivered by Grant Cogan, who's an associate, and Stephanie Tabb, who's a computational design specialist. So I'm going to tell you a little bit about our first presenter, Neil Katz, who's going to be presenting on SOM's history of innovation. Neil Katz is an architect, works with interdisciplinary project teams on design, analysis, and documentation, with a focus on the development of computational tools and processes. He leads the computational design group in the New York office. In addition to project work, Neil has led and participated in research groups and initiatives focusing on computation, structures, and high-performance design. He teaches computational design concepts and tools at SOM and various colleges, and lectures widely within the larger design community. At the core, his work are research, development, and applications connected to algorithmic, parametric, geometric design modeling, solar and energy analysis, zoning analysis, developing and implementing standards such as graphic and organizational, and patterns. So welcome, Neil.
Thank you. So as a prelude to some of the exciting research that we're going to be discussing today, I'm going to give a quick overview of SOM's history of innovation, focusing on computational design. Since the 70s, SOM has explored and experimented with computational devices as tools to enhance our process of design and delivery of our projects. There was no off-the-shelf tool available at that time, although there was research in this area also taking place in academics such as Cornell University with Don Greenberg. SOM decided to take on their own research and develop a set of tools. The set of tools with names like Draft for modeling, Plot for printing drawings and images, Render for visualization, SDMS for structural analysis, and several others, were developed in collaboration with architects and engineers who were eager to use these tools as they worked on actual projects. If you visited SOM's office in the 1980s, you would have seen equipment that you would probably not have seen in any other architectural firm. If you visit our offices today, in terms of equipment, there's nothing extraordinary. But innovation, of course, is more than hardware or even software. While there are experts in the office using and developing tools and technology, our goal, since we started developing our own software, has been to distribute the use of these tools and even the development and workflows that accompany them among teams working on projects. At the time of the development of our proprietary tools, SOM had offices in 9 cities in the United States. And as an example of the potential of these tools, we created a video of fly-throughs of our models of each of these cities. Images, animations, VR, visualizations of our projects today in their urban context are often indistinguishable from photographs, so very different from what we were doing 40 years ago. In addition to photorealistic visualizations, we use many visualizations and documentation techniques, capturing physical aspects of our models, as well as aspects which are not visible. The hash terminal in JEDA is an early example of the use of our computational design tools for both architecture and structural design. A more recent aviation terminal is an example of applying innovative computational thinking and tools on contemporary projects. These 2 projects share a dependence on both engineering and architectural expertise, on innovative use of materials, a focus on sustainability and natural daylighting, and on computational thinking and computational tools. There are a few projects which have spanned many years at SOM and living through many changes in technology and innovative processes. Moynihan Train Hall, an adaptive reuse of a landmark building in New York City. The design process spanning about 20 years has been modeled and designed using SOM's proprietary software at its beginning, then using our customization of AutoCAD, and then taking full advantage of BIM using Revit. From modeling the existing structure with help of laser scanning to collaborating with engineers specializing in lightweight structures, this project has been a successful experiment in applying innovative processes and using and developing innovative tools. Even the fabrication of the skylights of the Moynihan Train Hall requires substantial expertise in geometry, engineering and analysis, and documentation. Interdisciplinary collaboration is a distinguishing feature at SOM. Even at its founding, Louis Skidmore and Nathaniel Owings were architects and John Merrill was an engineer. Bruce Graham and Fazlur Khan continued in this tradition, and the Hancock Tower is just one example of many. And this philosophy and culture is as strong today as ever. In 2017, SOM created an exhibition for the Chicago Architecture Biennial, which showcased the contributions of SOM's engineers, whom we also call designers in architecture. And our engineers have also collaborated with other architects and many artists. In addition to the gallery of SOM building models, in which only the structural components are shown, because the structure is such a distinguishing feature of our work, each one of the models is immediately recognizable. And the towers are arranged in size order, so the structural innovations to enable unprecedented heights are apparent. We also showcase some of the research that we had been doing and are still doing in structural design. An ideal example of the collaborative nature of SOM's practice, another one and process is the Penn Station 33rd Street entrance canopy. Form finding with structural analysis tools and close collaboration as well with fabricators have led to this gem of a subway entrance at one of the busiest subway stations in Manhattan. Another example is the Lotte Tower, a mixed-use building with a distinctive diagrid, which varies from bottom to top, as does the floor plate. In addition to innovations in the design of the Lotte Tower, we also developed and documented in this paper a method of sharing project information, not only among project team members, but also among the various tools that the team was using. Interoperability, which SOM designed into our own tools in the 70s and 80s, because we needed to, became a challenge as we began to use different tools for different applications. The Wang Chao Center demonstrates how a computational design process is able to take into account and design for the many aspects of a tower. As we add more criteria to the design, the model accommodates. Where there are conflicts, we must evaluate the trade-offs and prioritize. Analysis tools assist in these decision-making stages. The Kathleen Grimm School is an innovation in sustainable design, a net zero energy elementary school in New York. Since our founding, sustainable design has been an important consideration and is currently a key design factor in every project and the focus of many research initiatives, and you'll see some of them today. Nathaniel Owings in 1969 said, "Civilizations leave marks on the earth by which they are known and judged." In large measure, the nature of our immortality is gouged by how well their builders made peace with the environment. There's a strong internal collaboration within SOM on projects and on research. We also collaborate externally with other design and technical professionals, with builders and fabricators, government agencies, and academic institutions. Another interesting example, an interest in origami among several engineers and architects at SOM led to this innovative pavilion, and applications in buildings that are dynamic in the projects that we design are inevitable. To sum up, there's much to be learned from experience, and SOM's legacy and innovation in computational design, among many other aspects of design, documentation, materials research, sustainability, and construction, provides much material and inspiration for us at the firm today, and many others in the field, from students to professionals. Research and innovation is sometimes blue sky, but most often project-focused or project-inspired, enabling us to explore ideas that improve a process, design a better project, increase efficiency, both of our process and also of our projects, and expose forms and ideas that would otherwise be unexplored. The scale and complexity of many of our projects necessitates many aspects of research, from structural systems to design workflows. At SOM, we share a passion for the projects we work on collaborative, interdisciplinary environment, and for the research which spins from these projects and then gets applied to many projects in many ways. The following presentations will reveal a varied set of research initiatives at many scales, touching many disciplines. They're representative of the vast interests at SOM and the culture of our practice, which allows and encourages these innovations and initiatives to happen.
Thank you so much, Neil. So we're going to move on to the next presentation now, which is titled Spatial Laminated Timber. Sorry, we have two presenters, Benton Johnson and Kyle Vansis. I hope I'm pronouncing your name right. Benton Johnson is a director of structural engineering in the Chicago office. He brings new approaches to structural engineering and sustainable design through research initiatives and industry partnerships. He leads SOM's Timber Tower Research Project, a multi-year initiative involving full-scale structural, fire, and acoustic testing of mass timber systems. He has also emerged as a leader in 3D printed buildings through collaborations with Oak Ridge National Laboratory and the U.S. Army Corps of Engineers. His innovative approach to structural engineering results in efficient and sustainable solutions that are applicable to a wide range of building types. Johnson's projects experience includes a range of domestic and international projects, from super tall buildings, mixed-use developments, and commercial offices, to convention centers, healthcare facilities, and demonstration buildings. Notable works include 100 Mount Street in Sydney, Nanchang Greenland Exhibition Center in Nanchang, China, the Billie Jean King Main Library in Long Beach, California, Christ Hospital Joint and Spine Center in Cincinnati, Ohio, and the C.H. Robinson Midwest Headquarters and 330 North Green Street in Chicago, and a 3D printed AMIE 1.0 project in Oak Ridge, Tennessee. Johnson is a member of several industry organizations, including the American Concrete Institute, the American Wood Council, the American Institute of Steel Construction, and the Structural Engineers Association of Illinois. And now I'll introduce Kyle Vansis. Kyle is an associate design architect supporting the vision of design leadership. His dual background as an architect and engineer allows him to think of projects holistically. Through his understanding of general project design philosophy, details, and construction techniques, Kyle helps coordinate work with other project team members in compliance with project standards and procedures. Kyle is also a researcher in design computation and fabrication. And part of the collective, he has led fabrication of stereoform slab and 2-scale concrete prototype using advanced robotic fabrication techniques. So please start your presentations.
Okay, thanks, Daniela. So as Neil was saying in the introduction, these projects that you're about to see are kind of where all of that innovation historically is now leaving us, and hopefully you see kind of contemporary examples of the evolution of what Neil presented. So he talked about the 2017 biennial. We also participated in the 2019 biennial, which was stereoform slab, Daniela mentioned, which really, I think, began this, at least 2 biennial now, tradition of creating pavilions for the biennial that are also building demonstrators and building prototypes. And so this prototype looked at how we could rethink the conventional concrete slab to be kind of more materially efficient, but also to fit within existing construction means and methods within the city of Chicago very specifically. So we really thought of it as a material innovation that was highly pragmatic, beautiful and expressive, but also an incremental innovation. And we talk a lot here at SOM about incremental innovations. What is the right amount of innovation? So that was 2019. Now let's, where did this come from? This came from the legacy that SOM has of digital meeting material innovation. A lot of the projects that Daniela mentioned in response to, or in Benton's bio, are projects where we're trying to bring what we can imagine out of the computer and use advanced fabrication to make them a reality, make it a material reality. And so we've been working with the University of Michigan over the last 3 years in a series of workshops, but also studios, where we're looking at things like robotic stereotomy and robotic slip form casting, and more recently, timber manufacturing, and how, always we can look at what's going on in the lab and how that can scale to a manufacturing level and get directly into the construction industry. So we have this idea of a building demonstrator that we've been deploying at the biennial, but we also want to fit into the biennial's key themes, right? And this year, it was all about finding innovative ways to utilize what is traditionally underutilized and underinvested spaces in the city of Chicago. So the Available City was about getting out into the city, decentralizing the biennial and making it much more about the people that don't normally interface with architecture. And so we partnered up with Epic Academy, which is a charter school on the south side of Chicago, to build an outdoor classroom. So there's always this kind of dueling prerogative or dueling goal. And so again, what would the lightest weight timber slab look like in the context of an outdoor classroom? And when we started to design an outdoor classroom, we found that the mission was actually quite different than what we initially expected. What we initially expected was that we needed to create a space outdoors that was adjacent to the school within its grounds, its property line, that would support certain pedagogies that you might want to be focused outdoors instead of indoors. But in reality, and especially on the south side of Chicago, it's about creating a bridge to the community. And breaking down the barriers. There's this kind of weird interstitial space between the school and the community, and it's sort of no one goes there. And Leondra Khan, who's the executive director of Epic Academy, was very much interested in this being a space where the community and students would come together. And this is really important, especially on the south side of Chicago, where University of Chicago and other institutions, schools, they're large brick buildings, very monumental, and there's this kind of tradition of maybe a bit of separation between the school and the community. So there's already been a number of classes and partnerships with Chicago State University. This was so Epic Academy has a really cool drum line, and this was a workshop that Chicago State had done in conjunction with that drum line, looking at more traditional African American drums that were developed in the United States of the African lineage. But okay, let's get back to technology. So when we look at the future of timber construction, we're really looking at kind of somewhat oppositional systems, right? We have conventional structural framing, and this can be anything from 2x4s that you see in residential construction all the way up to 8x8s and LVL, larger timber members. But they typically span in one direction, right? Whereas CLT is more flat plate construction and is less materially efficient, but spans in two directions and also does some of the things around acoustics and fire protection that are needed in commercial buildings. Ben, I don't know if you were wanting to hop in there, but.
Yeah, no, I mean, there's this, this kind of tension between, lightweight and traditional versus really, really heavy. And really the exploration is there some missing ground in between the two? And that's what Splam looks at.
Yeah. And this really, this goes back to what Neil was talking about earlier, but I think the timber research project is 10 years old now or something like that.
Like 8, yeah.
8 years old, and it was one of the so the first investigations Ben led on using CLT at a high-rise level. So we're definitely excited about CLT and its potentials, but we wanted to use this project as a way of finding a sweet spot in between conventional framing and CLT. And as designers and engineers, or designers, as Neil said at SOM, we often start in a place like this where we're looking to find optimal ways to materialize a structural system. So what you're looking at here is a very abstract representation of the stress flow within a conventional office floor plate, a typical 30 by 30 foot column span.
Yeah, and so go ahead to the next one. Yeah, and so as Kyle was mentioning, what we're trying to do is really find that sweet spot between conventional framing and super efficient structures. And we did something similar for stereoform, where we're trying to find what is the right amount of innovation. Certainly on the left hand side, having uniform joists is not the most efficient thing, but it's easy to build. All the way on the right hand, an extreme example is curved joists following the lines of principal stress. Much more efficient, but a lot of complexity. And so really, what is the right amount of complexity that can drive the changes we're looking for? Go ahead to the next one. And so, Kyle mentioned, we're trying to find the lightest weight timber slab out there. And so, CLT is great, but it's a solid uniform mass of a single thickness as it makes it span. And what we like to do is look at more optimized forms. So on the left-hand side is an analysis run using topology optimization, density method, where we're moving material from areas of low stress to areas of high stress in the red. And we did this analysis for the Splam pavilion, and then just kind of trace over it to find where we should be adding materials. And the sketch all the way on the right-hand side is kind of our interpretation of that analysis and how we can increase and decrease the thickness of the material to make it more efficient for that span. Go ahead. And so this little GIF shows you the kind of process as we're taking material away from locations where it's not really being fully utilized. And what you see, similar to the stereoform slab, is you get a concentration of material near the supports, and the material goes away in locations all the way in the middle. Go ahead. And so after we applied this process to Splam, you can really see the value here all the way on the right-hand side. You can see that the material is carved away from the middle. And what we're able actually to do is get something that is competitive in terms of the thickness with CLT, but using an amount of material that's similar to like conventional joists. And I know you wanted to mention something on this, Kyle.
No, I want to make sure you saw the slide.
And so I really like this video where it's zooming out here, because it really shows what the thing is all about, right? It's like pulled right from the computer. You see the gaps in the middle where there's low stress points, and the density increases as it moves towards those columns and those four support points.
Yeah, the result is.
Go ahead, Cal.
Yeah, sorry. But yeah, so this is a bespoke design, right? We designed it for this space, for this school, but we have ambitions to take this into a more modular level. And so to do that, we really focused with Michigan on a prefabricated modular system for timber joinery. And so here you see Wes McGee and Tien and a few of the students that worked on this project over the summer with us. This was a year-long studio, but it went into the summer, and fabrication actually took place in June and July with an opening in August. And we really got scientific about the joinery. It turns out that in these systems, the joinery is the most critical spot in terms of stress concentration and shear transfer. So we worked with the civil engineering department, and we got out our Japanese joinery books, and we found, we tested a number of different, prototyped and tested a number of different joinery types, and then brought that information, those results, those empirical results, into our design models, and used that to optimize actually the types of joints and the number of members and the number of unique joints. And so here you can see a 5-axis mill creating what's called a scarf joint. But it's actually a kind of dual joint. There's a scarf at the end and then a lap joint. And the lap joint is just a minimal depth joint, really to help with dimensional tolerance of the system overall. I think we've all probably used 5-axis mills. They're out there. But I think what's exciting for us in this is that this is really where timber manufacturing is at its most innovative. Is prefabricated systems where they're using, Hundiger or another kind of large scale fabricator provider of 5-axis milling to create complexity and joinery and other parts of the system. So we see this again as a one-to-one with two-scale manufacturing. And so as I said, we used this data and also used kind of a feedback with the structural model to understand unique types. And we ended up with 912 total members, 50 unique types. And our goal is to minimize the number of unique types. The more we can do so, the more efficient it becomes from a constructability standpoint. But obviously, the trade-off with that is the ability to approximate an optimal topology and to create hyper-responsive systems. So there's this kind of back and forth between kind of uniqueness and standardization that we're trying to explore. And here they are, 912 members getting ready to be shipped to Chicago. And here it is in built form before the roof. So yeah, it's quite beautiful, quite expressive. And if you ever wondered to yourself what the lightest weight timber slab for a commercial building might look like, well, here is something probably pretty close. With that, I'll let Daniel take it away.
Thank you. Thanks for that presentation. Okay, so next we have Daniel Inocente, who's going to be presenting on Moon Village. And Daniel is a senior designer in New York. Before joining SOM, Daniel worked for Gary Partners, NASA, and HKS Line, or LINE. He works with multiple teams across SOM's international offices and projects, including Zhuhai, Shizu Bay Tower, Tour Charenton, and more recently, a proposal for Neom Airport. Daniel is part of the New York Design Science Computation Group dedicated to researching and exploring materials, manufacturing, design processes, and computational methodologies. He worked on a variety of building types and projects since joining SOM. His interest in space architecture and cross-sector research has led him to initiate and foster partnerships with government, academia, and industry, including the European Space Agency, MIT, Lockheed Martin, Blue Origin, and University of Manchester. So welcome, Daniel.
Thank you, Daniela. Can you see my screen?
Yes.
Perfect. So I'll talk about a collaboration that we had with ESA called the Moon Village. SOM, ESA, and faculty at MIT first established a partnership in 2018 to explore aspirations for a permanent lunar settlement through cross-industry collaboration. The idea for a Moon Village was first presented by the ESA Director General, John Werner, who inspired the partnership to envision an open architecture based on global cooperation for sustainable human exploration. So the multidisciplinary project focuses primarily on principles of resiliency, self-sufficiency, and next-generation integrated habitat architecture. So just to talk a little bit about space architecture. Space architecture is a really incredible vehicle for cooperation. For example, the ISS, which has been in orbit for more than 2 decades, has been humanity's research station in space and has hosted hundreds of astronauts from more than 18 countries around the world. It is a platform for science and has transformed our understanding of human biology, material science, climate science, and the universe in very fundamental ways. And at the same time, space exploration has made major leaps in the last couple years, with private companies developing and proving new transportation systems, and even creating and engineering an entirely new architecture for heavy lift vehicles like the Starship by SpaceX. But these are just a couple of examples of some of the more recent achievements by the space industry. And so one of the questions we started off with was, why the moon? Well, out of all the celestial objects in our solar system, the moon is the most accessible, with launch windows at any time. The moon is also a laboratory of planetary science with a deep geologic history going back to the formation of planet Earth. The history of the moon is also the history of Earth, where dynamic processes make it difficult to access geologic history. The other important characteristic of the moon is that it is in synchronous orbit with the same face pointing towards Earth, which means that the moon's exposure to sunlight is near continuous. The moon has a spin axis, which is inclined by 1.5 degrees to the ecliptic plane. And this creates these kind of microenvironments at the polar regions where you have abundant exposure to sun, but also areas where you have permanent ice deposits, which is one of the interesting things that different missions have started to revolve around. So in January of 2020, a memorandum of collaboration was signed at ESA's headquarters, where we went to ESA's offices and we met with the Director General, and we signed an MOC to advance the cooperation that we had established since 2018. And so this led to a CDF study, which took place at STEC. And so a CDF study is ESA's concurrent design facility capability, where they can conduct a cross-disciplinary effort to really assess whether your technology is being developed in the most appropriate way. And the STEC team composition included experts from systems, mission architecture, structures, thermal materials and processes, mechanisms, radiation, power, life support, advanced concepts, just a wide range of different capabilities to really understand how the architecture that we were developing was performing. One of the key aspects of this was also thinking about future ISRU structures or in situ resource
I'm sorry, can I
structures.
interrupt you for a moment?
Sure.
Okay, there's a message on here that says you don't have permission to play this media. But this is,
there's no media here.
Presentation is being live streamed.
There's no media here.
Okay, I just wasn't sure if you meant the slides.
Okay.
Okay, sorry about that.
No worries. And so this illustrates, just some of the thinking about future architectures, where once you have an in-place habitat, you can actually make use of, that existence of a ready-made architecture to develop new technologies, new techniques, and think about how you can use resources that exist on the polar regions or in the equatorial zones. And so one of the greatest challenges for going to the moon is transportation. And in this study, we looked at a wide range of different vehicle architectures. We looked at some of them that currently exist and some of them that are being developed. And we try to size the architecture and constrain it to the vehicle performance criteria. And we also studied a wide range of habitat architectures, most of which exist on the ISS. And the ISS is currently composed of more than 16 pressurized modules, but those are primarily made from aluminum isogrid structures. And there's also other types of materials being used, lightweight materials, composite materials like Kevlar and Vectran. And so, although Kevlar has been used in the past by NASA to study how inflatable structures could become space habitat architectures, for this study we looked at a material called Vectran, which is 5 times stronger than steel, but 10 times stronger than aluminum by weight. And so the architecture that we developed became this hybridized system where we have a combination of both metals and composites coming together to work as efficiently as possible to create this sense of space and just basically create an environment where astronauts and the occupants can really do the work and the scientific experiments that they need to do. And so we established, very rigorous methodology to approach the problem. First, by looking at, what are the concept of operations, what are the system design drivers, and then what are the criteria that we're actually designing around. And then the mission phases, obviously, there's a lot of things going into play here because space architecture is very complex. But when you think about space architecture or just any, space-rated vehicle, you have to think about testing. How do you launch it? How do you transport the vehicle? How do you land it? How do you deploy it once it's on the surface? And then how do you transfer it to its final building site where you can assemble and operate it? And then in terms of human factors, there's a lot that goes into thinking about how you can engineer an environment for its occupants. Things like visibility, lighting, atmospheric pressure, temperature, humidity, physical mobility, just being able to move through the spaces. It's because you're in a reduced gravity environment. And so that means that you have to think differently about the interfaces. Things like stairs have to be designed differently. And also just in general, thinking about material selection and how you can create a very safe environment for its occupants. So there's definitely a lot of different factors that you have to think about as you're designing these kinds of spaces. And so these images just illustrate the two types of environments that we were primarily focused on. One was the working environment, and the other one was the living environment, where the living environment has to integrate as many technologies as possible. So there's some way of approaching architecture where you're starting to think about the machine to human interaction. And there's a lot of embedded technologies in your surfaces, in your geometries, in your materials. And that really helps remove all that equipment from the spaces where you typically see that on the ISS. And so, we really try to plan this in a way where we can think sequentially about the logistics. So in its pack configuration, the outer shell actually comes in, but once it's deployed, all the equipment, the racks, all the things that are being used for experiments, all of that has to be projected to the perimeter, but it's also supported by a floor system that is kinematic and tucked in underneath the primary floor structure when it's launched. And so the habitat, really aim to address functional, environmental, and performance constraints, but also place an emphasis on human-centered design principles, which are characterized in the architecture, which is expressed by the unique hybrid structural system. The result was a net habitable volume of 390 cubic meters and a net habitable area of 104 square meters. One of the things that allowed us to do this was that the primary mechanical systems were located within the composite floor assembly instead of in the core where that has been studied in the past. And the payload racks units are mounted near the center, like I mentioned before. And then once it's deployed, they're pushed to the perimeter. And that actually improves the environmental performance for other reasons, which I'll talk about in the next slide. And that has to do with radiation. because radiation is one of the biggest challenges in space. And so there are already some standards for radiation. NASA has set, different limits for different age groups depending on the kind of exposure. The kind of exposure is very different when you're on the ISS, for example, compared to when you're on the moon. And that has to do with the amount of material between you and the outer space environment. And so we also studied the kinds of materials that would be the most beneficial for helping mitigate irradiation. And you can see here that we're actually using a software, which is an open source software called Oteris, to look at how metals, how other composites perform under radiation. And the one thing that we've discovered and at the same time has been documented pretty well is that materials with a lot of hydrogen really help improve the reduction of radiation. And so if you can bring materials together in a very unique way, you can actually help improve the overall performance of the architecture and increase the mission duration. That's why when you put more material between you and the outer space environment, it actually helps improve how the architecture is performing. And so here you can see that we thought very carefully about how this window structure and the composite shell came together. And I think what's really clear here is that there's a lot of layers that go into this assembly. And one of the most complicated things which we studied was also thinking about how you pack this assembly, because it's not just a shell, it's also, you have to think about insulation, you have to think about impact protection, you have to think about pressure seals, and then finally you have to think about the materials that the occupants are interfacing with. The other really interesting aspect of the research was we looked at different life support systems that are in existence. For example, on the ISS, they have different technologies for oxygen generation, for water recovery, and also they have these modules for things like hygiene and just being able to discard waste. And so these are the kinds of racks that you see on the ISS. But more recently, ESA has been developing advanced life support systems where you can actually take oxygen, you can recover, you can actually take the carbon dioxide that is being produced by the humans, the occupants, and you can recycle it and you can compact the system into much smaller units. And then the other generation of technologies that are being developed is food production, because that's going to be something that's very important in space. How do you help supplement the nutrition of astronauts once you're out in space, whether it's through things like algae or spirulina, or even higher plants that can be grown inside of large chambers. So these are a few of the different technologies that we thought about thinking of integrating into the habitat architecture. And then one of the more, I think, interesting findings was that power, even though there is a lot of exposure to sunlight at the poles, power is still really hard to capture when you have a lot of mass associated with it. So for one habitat system, we needed 59 kilowatts to operate the architecture. But a solar power system, including all the solar panels, the batteries, all the equipment, all that together weighs about 60 tons, which is a lot more than when you look at something like a fission reactor system weighing at about 5.6 metric tons. So when you think about the different technologies that exist out there, fission reactor systems could potentially make the difference between habitat architectures and not having them. And so after all this work that we had done, studying the architecture, we were invited to the Venice Biennale to bring this idea of the Moon Village to Venice. And we ended up designing and redesigning and engineering a habitat that would become almost like a pavilion for people to come in and experience what this environment could feel like. We put a lot of really interesting features into it, things like illumination controls, displays. We even tried to recreate some of the materials in a unique way. And ultimately, although we did not build this habitat architecture, we did exhibit a lot of really beautiful models and put together an animation to showcase all of the thinking and the engineering that went into this project. And so finally, we produced an animation. It's a 4-minute long animation, which you can find online. It's a really beautiful way of characterizing the way that we had envisioned this taking place. And that's all.
That's great. Thank you so much.
Yeah.
Great. I can't wait to discuss all these great projects you guys are presenting. The next presentation is Georgie Petrov. He's going to be presenting on 3D printed structural components. And Georgie Petrov is a practicing architect and structural engineer. He's a senior associate principal in the SOM Structures Group at the New York office of Skidmore, Owings, and Merrill. Georgie works on high-rise projects, long-span roofs, and specialty glass and steel structures in North America, Asia, and Middle East. Georgie is a leader in pioneering SOM's involvement in design for structures in outer space and in developing novel projects delivery method. He's licensed as both an architect and professional engineer and as well as an adjunct professor at NYU's Tandon School of Engineering. Georgie led the structural design for One Manhattan West, a new 70-story office tower in New York City, located in the challenging site rising above the active train tracks. This constraint was turned into an opportunity by sloping into the perimeter columns to the core, creating a column-free lobby at the base of the super tall tower. Another notable recent project includes Terminal 2 at Kempegowa International Airport and Bangalore, India, King Abdullah Financial District Conference Center in Riyadh Kingdom and Saudi Arabia, and the 400-meter tall Shenzhen Sham Yip Tower in Shenzhen, China, which features a ladder core and a brand new structural system for super tall skyscrapers.
Thank you very much for the introduction. Can you guys hear me?
Yes.
Excellent. This next project that I'll show is actually a nice pairing with the story that Daniel just described. In that when you go onto this these steps of different research, one idea leads to another and leads to another, and there's a great growing of knowledge that we gain over manual projects. And so when we got invited to build a full-scale mock-up of our moon module in Venice, we decided to use the opportunity to do some explorations into manufacturing as well. And one key part of designing for space is that you have to be on that scale of optimal efficiency that Ben talked about earlier, because the astronomical price of taking material out of Earth's gravity field really requires optimal efficiency. These exciting new developments in additive manufacturing over the last few years is something we wanted to explore. And the typical materials that are very familiar to everybody of the various plastics and powders and even concrete, although great for prototyping and materials on Earth, we needed something that's ductile and very strong that could be manufactured through 3D printing. And well, when you think about it, welding is a way of delivering a small amount of molten metal in a precise location. And if you can take a welding torch and attach it to a computer-controlled robot, then you can do 3D printing in metals. And our contacts at the European Space Agency introduced us to this company, MX3D, out of the Netherlands, that specializes in doing exactly that. They've gotten recently a lot of press for this 3D printed steel bridge that they designed. They've done several other projects like this, where you're taking a typically designed machine part, figuring where really the stresses are and optimizing it. And for our Moon Village Pavilion, we decided to explore this to manufacture the floors of the module. And what we did is we started with the design space, which is the overall layout of our floor. With that, we figured out where we want to support it in the vertical structure, in the same analogy as the actual bit that would fly to the moon. And we ran our optimization process similar to, again, the previous project that was shown, figuring out generally where you kind of want to put the material to be most efficient. Usually the results of these analyses are, you can't just take this color graph here and build it. So you have to go through several steps of rationalizing it and coming up with a pattern. So this was our first stab at coming up with a very efficient floor structure that would respond to exactly the loads and the conditions. But then we started playing around with the manufacturing process, and there's always that moment, right, where you do the design and then you have to make it adaptable and build it and change it to respond to how the construction process is actually working. And one big constraint is that, right, the 3D printing in metal, you're layering a molten metal that's droopy. And so there's only a certain angle from vertical which you can play with. And so we went through many steps, re-rationalizing the geometry to work well with both the aspirations of the optimization, but also the capabilities of the 3D printing process. And so we divided the floor into a number of parts, and that was partly governed by the reach of the robots that MX3D had. And so we had modeled all of the 3D printing steps, the angles, the way that all the beads would be layered, and then make sure everything fit within the reach of the robot in order to make sure that this could all be printed correctly. And so these are the two types of pieces that were repeated several times, each tested before we started printing. We had to then come up with ways to take the 3D printed material and marry it with the more regular construction of the rest of the habitat. And so we came up with this idea of a typical edge piece that would hold the 3D printed material. We then went through several layers of more optimization to make sure that we actually have the smallest possible members and the thinnest possible walls. The capabilities of the MX3D robots could do several thicknesses of the 3D print. And I think in the final resolution, most of the 3D printed material is made with just 3 mm thick beads of weld material. And this is the final design. It's how it would have been put into the capsule. Another interesting bit is the way that the jointeries and the transition from one element to the other is. So we did a lot of these mock-ups of printing different way the branches go from one another. Because right when you're printing on the straight branch, it's pretty straightforward, but how exactly you transition, and always having in mind that you're dripping a molten piece of metal and you can't let it fall. This is, you can see a zoom in of one of these transitions and the frankly very beautiful pattern of the 3D printed material. And this is the final piece that we had manufactured of all the floors, and you see the final configuration of it. Thank you.
Thank you very much. So next we have Luke Leong, who's going to be presenting on Microbial for Life, Human and Nature. Luke Leong is the director of MEP and Sustainable Engineering Studio at SOM. Leong leads his team in attaining the highest levels of human, environmental, and financial performance. He has won multiple awards, including 8 Excellence in Engineering Awards from the American Society of Heating, Refrigeration, and Air Conditioning Engineers, ASHRAE, both Beyond Green Awards from the National Institute of Building Sciences, and several Sustainable Design Awards from the American Institute of Architects. Project highlights include the Burj Khalifa, currently the world's tallest man-made structure, Roche Diagnostics in Indianapolis, the Greentown Qingdao Tower, and the Zhengzhou Greenland Plaza. And more than 40 LEED certified or registered buildings, including LEED Platinum building with the first large-scale horizontal wind turbine in Chicago. Luke is a LEED Fellow, ASHRAE Fellow, and Centennial Fellow from the Penn State University Architectural Engineering Department, the chair of the ASHRAE Environmental Health Committee, commercial team lead, ASHRAE Epidemic Task Force, embodied carbon LCA work group leader, ASHRAE Task Force in building decarbonization. And I'm going to stop here because this is a very long bio, and I'm going to ask you to take it away.
Thank you. From the moon village to 3D printing, from the highest tech to the single microbial, that's inside the range of research in SOM. Earth to earth, dust to dust. The microbial in soil create the plants and the ecology around us. And in many ways, it provides food where we came from. And one day you and I will go back to the soil. Looking at Chicagoland, about 8,000 years BC, it is very different. It is made of covered grassland and then forest in the green. The grassland is kind of the yellowish color. But that changed. A lot of them has gone and replaced by urban area, which is the bright red. And kind of the less bright red, the orange color is actually farming. Now this farming oftentimes is not sustainable and carry a lot of runoff as in nitrogen and phosphate into the Gulf of Mexico and create hypoxia, which damage the ecology and also the water system in the Gulf of Mexico. If you think that only happened in Midwest, look at this. It's actually a phenomenon of the world, modern farming. And if you think that element only flows into the ocean, think twice. It also flows into the tummy of you and I. Why is that? At one time in pre-industrial revolution, that's this cycle of food and waste, which is got disrupted in in modern day farming. There's pesticide, insecticide, and also fertilizer inject into the soil to create a different sort of system. So this stuff actually goes not only into the Gulf of Mexico, but into the tummy of you and I. That's why if you look at the tummy microbial makeup of the pre-industrial revolution people, well, we cannot go back in time, can we? But we can look at the Amish people, and their lifestyle is going to be close to what it was. Compared to today's human beings in typical US, their microbial makeup in the tummy is very different. And the microbial tummy is important. It adds up to about the size of a mango. So that's how much microbial you have in your tummy, add up to the size of a mango. But it controls your immune system. It helps to digest your food. It helps your brain development. And it helps to eliminate pathogen. Oxford University in UK came out with different study, and one of them suggests your gut bacteria actually linked to your personality is actually mental. Sometimes you think the world is changing. It's not necessarily the world. It can be you. But there are other times when you think the world is changing. It is actually the world is changing. And also, if the guy next to you acts funny, Well, don't immediately blame him. It could be his gut micro or her gut micro not doing its job. More interestingly, recent century, about 100, 200 years, we find out the rapid increase of chronic disease from asthma to allergy to, think about it, there's a person in our office allergic to chicken. How did that person go through the evolution if he or she is allergic to chicken? So there's some things going on here. And what we see here is the gut microbes actually can impact diabetes, asthma, cardiovascular diseases, and also mental health disorders. Some of you may immediately have an idea that, well, maybe we will implant some of the gut microbes from the other humans to the one that is sick, and maybe we were able to do something. Well, you're not the only one. There's already medical research go down that road. In this case here is Johns Hopkins University. They actually transplant some microbes in the digestive system of a human being, a healthy one to the not healthy one. And they use this routine regularly, and the cure rate is over 90%. So we can be what our gut microbe is. By now you're thinking, I'm not a doctor. I'm not a person dealing with healthcare. I'm a design architects and engineers. What can we do? Well, you know what? It all starts from the soil and the regenerative farm. So if we start specifying biomaterials to minimize our embodied carbon, and more importantly, make sure the biomaterial is from regenerative farms, not from farms that grow with insecticide, fertilizer, and all that, it will help. In fact, in COP26, SOM put forward the idea of urban sequoia, a new types of building that's gonna generate plants and also capture carbon using regenerative method to change the environment and human beings. Not only in the buildings, we also have to change our farm. From the current days, only 5% farms are generative to all our farms are regenerative. In that way, we will minimize the nitrogen and phosphate runoff to the Gulf of Mexico. And remember that not just a North America problem, and it's a global problem. So we create a healthier environment. Not only that, we can potentially create a new generation of human that is much healthier than the one we are experiencing. So yes, architects and engineers with regenerative farm, we can save the environment, create healthy people, and yes, we will save the world. Thank you.
Thank you. Thank you, Luke. So next presenting are Daniel Zweig and Justin Leong that are going to be presenting on wildfires. Daniel Zweig, AIA, has technical design experience for projects across California and the world. Educated in Chicago at IIT, he received his BArch in 2014 and his California architectural license in 2016. He has extensive experience coordinating multidisciplinary teams in each phase of the design, from concept to construction administration. He has the macro experience of building code designs, diagrams, high-rise codes, and lead coordination, as well as detail experience in interior and exterior architectural systems. And I'm going to introduce Justin Leong, who's an associate urban designer at SOM Los Angeles office. His creative work on large-scale mixed-use projects respects the authentic culture and unique environmental characteristics of every site. His work includes conceptual master plans focused on human experience, with a preference for the complex challenges of urban redevelopment, for connecting the past with the future, and walkable urban districts within civic infrastructures of public open spaces. His wide range of urban design projects in North America, Asia, and Australia and Latin America, including campus master plans in universities, hospitals, social affordable housing in neighborhoods. Take it away.
Thanks, Daniela. Justin and I are here to present SOM's research on California wildfires. So over the past several years, SOM has been investigating wildfires in California specifically and asked how, as architects, engineers, and planners, we can do more. Earlier this year, we published a document summarizing the data we've collected so far, coupled with conclusions and a set of guidelines for more enlightened wildfire mitigation strategies. We definitely don't have all the answers, but want to be part of the conversation and contribute to making our communities more resilient to wildfires. Today, we'll share a few pages from the published guidelines where we look at fire mitigation measures at 3 different scales: the wildland scale, the urban scale, and the building scale. So Justin will touch on some of the history.
Thanks, Dan. So these first few slides are from the introduction of the published document. We started this project by trying to understand the history of wildfires in California. And everyone knows wildfires are no longer just an occasional natural disaster. They have become a season in the American West. And it is also increasingly becoming a global issue as we are witnessing many wildfires happening around the world. And looking at the past history, fire has always been a part of American West landscape, as Native Americans have been using fire for over 13,000 years to renew food resources and reduce the risk of larger and more dangerous wildfires. And many of the large and destructive fires that occur today are directly related to different eras of forest management in the US history. In 1850, the US government outlawed intentional burning and required that all fires be extinguished as quickly as possible, which basically allowed for forests to grow and densify without any proper management. And this continued on until the National Park Service and National Forest Service started to allow and mandate controlled burns to manage forests again in 1978. So nearly 130 years without controlled burns led to an unprecedented buildup of fuel loads that makes today's wildfire larger and harder to manage. And Dan is going to talk a little bit about the recent wildfires and some of their numbers and facts.
Thanks, Justin. So these charts represent the acres burned each year in California from wildfires over the last decade, as well as the total number of fires, the number of structures damaged, and the number of deaths. 2028 alone accounted for over 4 million acres burned in California. 2021 is at about 2.5 million acres so far. In general, you can see that the amount of acreage burned each year has been trending upwards over the last decade, along with the number of fires, which dramatically increased in 2014. We included several precedents in the document online that I'll flip through. One of them was the 1991 tunnel fire in Oakland, California. This fire was negligible by today's standards at 1,600 acres, but it was one of the most destructive and the second deadliest fires in California history until 2017. Approximately 2,900 structures were damaged and 25 people were killed. Other precedents include the 2017 Tubbs fire. At the time, it was the most destructive fire ever recorded in California history, with over 5,000 buildings damaged. Also in 2017, the Thomas Fire was the largest in California history at the time. And in 2018, the Camp Fire set records for the most destructive, deadliest, and costliest fire in California history in Paradise. I'm sure many of you remember that fire. In 2020, 650 lightning fires started on the same night in August. This was the time lapse that we were showing at the intro slide. The August complex was just one of those fires, and it became the largest of those, burning over 1 million acres, which is more than most years combined. So how did we get here? A key driver is climate change. The fire season starts earlier and ends later each year because of reduced snowpack and earlier snow melt. Most of the West experiences a dry season for part of the year where we receive 0 rainfall, which probably surprises most people in Chicago. These dry seasons are more intense and have extended by 75 days across the Sierra Mountain Range over the past few decades. In addition to this, California has been experiencing more and more drought, where our average rainfall during the wet season has been at record lows. As I mentioned earlier, we looked at these issues and guidelines at 3 scales. So we'll get into the first scale of SOM guidelines, Chapter 1, Wildlands. Justin.
Thanks. So here's a summary of the guidelines we published for the wildlands section. We'll focus on 3 of them today, but please feel free to look at the full document online and for other recommendations at this scale. So the first guideline that I will share today deals with the ownership of California wildlands. We learned that California's wildlands is managed by a number of different stakeholders. The federal government is responsible for managing about 58%, the state 3%, and then the remaining 40% is split among private individuals and Native American groups. So different ownership means that there are different resources and recommendations dealing with wildfires. So one of our guidelines is to recommend that all of these agencies come together to create a unified vision and strategies dealing with wildfire. So this will also help provide best resources and as to how to prepare for wildfire and how to work together to fight future fires. Moving on to guideline 1.3, as many of you probably know, about 50% of California's largest fires are caused by power lines and electrical equipments. So guideline 1.3, we recommend that, recommend to decentralize power sources in high-risk areas and use solar, wind, and other renewable resources to generate energy. And if we can eliminate the need for power lines to traverse through high-risk zones, then we can eliminate about 50% of major wildfires. Jumping to the last guideline that I'll share today is to bury all power lines that are within high wildfire hazard zones. These are the areas that were defined by the California Public Utilities Commission, highlighted in red on this map. And then we know that sparking equipment is extremely likely to start a fire in this zone. So interestingly, in July of this year, one of the California's most major gas and electric companies pledged to underground about 10,000 miles of power lines in the highest risk zones. So although this may sound impossible due to high costs, but companies are beginning to implement some of this idea. So we talk more about costs associated with wildfire in the full document, but to give you a quick summary, fighting fire and cost of destruction caused by fire is far greater than undergrounding power lines. So again, we have more guidelines outlined in the full document at this scale, so please check them out. And now I'll let Daniel to zoom in from the wildland scale and look at the guidelines in urban areas and buildings.
Right, so here's the summary of the urban areas chapter. We'll take a closer look at a few pages of data from the chapter and 2 of these guidelines. Explosive population growth throughout the 20th century has made California the most populous state. 1 in 8 US residents live in California. On top of that, housing in California is also approximately 2.5 times more expensive than the national average. These factors have vastly increased the number of people who move to the wildland urban interface, or WUI zone. Development in these WUI zones, number of houses and number of people all continue to increase at faster rates than in the rest of California. This leads us to our first urban area guideline: to increase the density of urban areas to reduce the number of people moving into the WUI zone. Cities need to prioritize infill developments and accessory dwelling units. With less homes in the wildlands, wildfires are easier to manage and allow for more controlled burns and other terms of forest management. Another topic covered in the urban areas chapter is city design practices. The 2018 Camp Fire in Paradise, California, mentioned earlier in the introduction case studies, was partly so devastating because people couldn't get out of the town during the fire. This overlay shows where Camp Fire started in the Northeast at 6 a.m. and then traveled quickly through suburban neighborhoods by 10 a.m. Main roads were blocked within hours of the fire. So another urban areas guideline is to require cities to implement fire staging, breaks, and multiple egress routes. Existing cities should consider how they can adapt their current communities to be better prepared for wildfires, and urban areas that have been severely impacted by wildfires should reconsider how that community is redesigned instead of just rebuilding in place. Chapter 3 is buildings. So here's a quick look at the issues and recommendations from the buildings chapter. We'll look at 3 key recommendations from this chapter. As I mentioned earlier, WUI is the wildland urban interface, the zone where buildings are most likely exposed to wildland fires. There are a number of WUI codes for fire resilient structures out there, and they've been shown to work during the last decade of wildfires. WUI codes only started being more strictly enforced and regulated in 2008. So the campfire, during the campfire, 50% of the homes that were built to these WUI standards survived the intense blaze. Only 18% of the homes that were not built to those standards survived. So the problem is there's no good visual representation of WUI codes. So guideline 1 for the buildings chapter is to provide better visual communication tools for these codes. Graphic depictions of these codes would help architects, builders, and reviewing authorities understand and implement the strict WUI code requirements. And then guideline 3 is for architects to provide affordable, adaptable, fire resilient building designs to make sure as many buildings as possible in California are fire resilient. Another key issue is the sheer number of people who are moving to WUI areas and the fact that WUI areas are the hardest place to fight wildfire. Fighting fires in forests costs approximately $800 an acre and $1,700 per acre in WUI zones. On top of this, the average home in California was built in 1950, long before WUI codes. So existing building codes in WUI zones are not required to meet current standards. These charts demonstrate the annual costs of wildfires. Just as a quick note, in 2018, the suppression costs were over $3 billion, and then the insurance payout was approximately $24 billion. The rebuilding costs were over $6 billion. Building guideline 4 is for governments and insurance companies to incentivize fire-resistant upgrades in high-hazard zones. This would offset the costs from fighting fires in WUI zones and paying insurance claims for homes destroyed by wildfire. The state has already started to commit to this effort, but more policy and incentives would help accelerate the process. So here's another summary of all the guidelines in the document. I know we've only touched on a handful of them today, but to summarize, this isn't just a problem for firefighters or for homeowners. Architects, urban designers, and planners all need to step up to provide affordable fire resilient buildings. Utility companies need to move the state towards decentralization of power. Governments need to prioritize fire resilient development and maintain the forests they're committed to managing. We hope this document helps clarify what steps needs to be taken. Again, this is a public document on som.com under the Research and Innovation tab. Happy to answer any questions at the end and hope that we can keep the conversation going. Thanks again.
Thank you.
Thank you very much. So now we're going to have our last presentation before we get into a panel discussion. And presenting are Grant Cogan and Stephanie Tabb, speaking about urban development predictors. Grant Cogan is design associate with SOM San Francisco office. Since joining the firm in 2013, Grant has been involved in design at all scales with a portfolio that includes education, cultural, commercial, and master planning projects. Grant is a key member of SOM's West Coast K-12 studio and has helped realize the vision of such prestigious institutions as San Francisco University High School and Head Royce. Grant has worked extensively with universities such as UC Merced, where he helped develop the 2020 master plan and led the design of the new dining pavilion. Grant's design approach is rooted in the spirit of collaboration and authenticity. Through close collaboration with his team, Grant seeks to give voice to the client's values and build environment, giving presence and performance to a unique vision. And then presenting with him is Stephanie Tabb. And Stephanie is a senior digital designer with Skidmore, Owings, and Merrill in San Francisco. She holds a Master's of Architecture degree from California College of the Arts. Prior to SOM, Stephanie worked for ELS Architecture and Urban Design, where she initiated the design technology group and led the computational design stream. And at Woods Beckett, she works across SOM's international offices on tall tower projects, integrating architectural design and innovative methods by leveraging computational design. In addition to project work, she has led and participated in global research and development initiatives focusing on developing workflow automation, facade rationalization, and computational methodologies. So welcome.
Thanks, Daniela. Hi, everyone. This is Stephanie Tabb and Grant Cogan, and we'll be sharing SOM's Urban Development Predictor project, which is an application of machine learning at an urban scale. This project expands upon machine learning research within SOM's architectural and structural practices, focusing on the largest scale of our work, the city. This research was conducted as part of SOM's Year 1 Accelerator program for recent graduates in 2018. For most of the team, this was a first experience with machine learning, and because of that, a critical goal for the research was to lower the barrier of entry for machine learning and encourage its future use within SOM.
Our research initiative was grounded in a fundamental question about leveraging machine learning as a tool for design and discourse between designers, developers, and policymakers. Although this research focuses in on a specific design question through the lens of San Francisco, this research is at its core exploration of process. How can machine learning disrupt the traditional means by which we discern patterns in something as dense and complex as the city? And we quickly discovered that the immediate benefit of incorporating machine learning into our design process was the granularity and precision with which trained machine learning models can discern patterns across vast quantities of data. Not only can a trained machine learning model provide a diagnosis of our urban fabric, revealing patterns and trends within our cities that might otherwise be hidden, but it can also provide a predictive lens by which we can see how design interventions and changes in policy might shape the trajectory of our evolving urban fabric.
That granularity afforded by machine learning at an urban scale allows us to challenge the broader strokes with which we understand the city, and to uncover data and patterns that might not fit neatly into neighborhood and district boundaries, allowing us to evaluate the impact of design and planning decisions on a more intimate property by property scale. In this way, we can more accurately understand the behavior of our urban environments. Our ability to understand the city through machine learning, however, can really only be as robust as the quality and scope of available data. Data and speculative design questions should inform one another to ensure that a model yields provoking and actionable insights.
For this research initiative, we were particularly interested in understanding the trajectory of San Francisco's rapidly changing urban environment. And one specific data set describing San Francisco's development pipeline became a provoking lens through which, given the aggregate characteristics of 10,000 properties submitted for development, a trained machine learning model could predict the likely areas of urban change in the future for the entire city. This data set became the foundation for predicting what we call development susceptibility in San Francisco, where a trained model would evaluate the remaining 200,000 plus properties of San Francisco and identify parcel by parcel which properties are most likely to be redeveloped at some point in the future. The trained machine learning model would broaden our definition of susceptibility beyond what district or geographic location a property finds itself in, considering all the attributes and features of a property and determining that susceptibility. And perhaps most importantly, it would help us understand which of these forces and attributes, or what we call features, would have the heaviest hand in shaping our cities.
In addition to the development pipeline data set, additional open source data was incorporated to comprehensively describe the various architectural and urban characteristics or features of every property in the city. And to provide geographic insights, the team also crafted additional data that describe spatial adjacencies and proximity to notable urban features like parks and public transportation. These spatial data sets include other critical adjacencies like proximity to seismic hazard zones and other features related to resiliency. This comprehensive and detailed data set is the basis by which the machine learning model will learn and then predict susceptibility.
The data set of known urban features and the target developments of development susceptibility also known, this research specifically implements supervised machine learning, where algorithms learn from labeled data sets to accurately classify data, discern patterns, and predict outcomes. Supervised learning in particular requires an active hand by designers, first curating a landscape of relevant data and defining a design question that is classifiable through which to train the model. And the model was trained by a random subset of pipeline and non-pipeline property data, after which the resulting algorithm was tested against a different subset of data to validate the accuracy with which the trained model could predict the known outcomes.
We trained 3 different algorithms, and the overall accuracy of the trained models was impressive, with only a few properties being incorrectly classified, as seen on the right. Between logistic regression, naive Bayes, and random forest, the differences in accuracy between the algorithms was pretty marginal. Our team elected to proceed with logistic regression as the backbone of our model given our interest in understanding the importance or weights of certain features, allowing us to more readily compare which urban characteristics, be it a zoning boundary or an architectural characteristic, had more weight in determining a property's susceptibility.
And the resulting model is visualized here, with each dot representing an individual property and its predicted susceptibility. Rather than produce a binary yes or no prediction of whether a property would be listed in a future development pipeline, the logistic regression model calculates the probability of inclusion in the development pipeline, giving us the opportunity to see where development is most probable, the big red dots, and least probable, the small blue dots. The prediction affords us a more granular view of how the city is projected to change. For example, when we zoom into the Mission District, as we see here, we can individually identify the properties that are most susceptible to change in a rapidly developing neighborhood. Although we would expect to see a lot of susceptibility, as we see here, along the major corridors of the neighborhood, such as Valencia and Mission Street, this granularity affords a pinpoint view of how one of the city's most rapidly changing neighborhoods is most likely to change in the future.
In a neighborhood like the Outer Sunset, we're looking at even the scale of a city block would assume zero susceptibility. The machine learning model unlocks the opportunity to identify individual outliers and other properties that would otherwise be disregarded or hidden.
Conversely, Soma is another development dense district, and many areas would typically be flagged for susceptibility. But the broader consideration of the machine learning model of features and predicting susceptibility affords us an opportunity to see which individual properties are most susceptible. Our hope in future developments of this model is to expand the predicted susceptibility to actually describe predicted architectural characteristics, such as predicted bulk and massing, area, use, and height.
One of the great benefits of developing a machine learning model is the continuity of data. We can deconstruct our robust database to understand the distribution and relationships between the various features, as well as the larger trends of predicted susceptibility as it relates to each characteristic of a property. These graphs also allow us to uncover surprising relationships. In San Francisco, we found that susceptible properties are likely to be located within seismic hazard zones. What is perhaps most important is our ability to understand why the city is projected to develop in a certain way and what is most heavily informing these predictions. With our model, we can understand the individual weights or importance of the various features that the machine learning model defined for its prediction. Here we found that a property's zoning district and permitted use played an overwhelming role in determining to which degree a property would be classified as susceptible to development. These weights, assigned and categorized entirely by the model itself, give us a fascinating glimpse into what shapes our cities most and begs the question of developers, designers, and policymakers. What if we were to shift these weights or prioritize developments for other desired outcomes?
And we did just that by taking the calculated weights of each feature from the machine learning model and manually adjusting them for 7 hypothetical development scenarios that you see here. What if zoning no longer played a significant role in shaping the development of the city? That's the second in the column there. And conversely, what if it had a much tighter grasp on the development, just to the right of that? What would a future San Francisco look like if we encouraged development near amenities like parks or promoted more density near public transportation? Infinite permutations of these questions exist and can be a powerful tool for designers, developers, and policymakers to understand at a granular level how changes to the underlying forces that shape our city might yield dramatically different futures. It is worth mentioning, however, that the manual manipulation of weights, as you see here, does sever the link to a true machine learning model workflow. Our research did include retrained machine learning models that selectively removed features such as zoning code and use and yielded conceptually similar results. We'll close with a proof of concept of what this research would look like if it were developed into an interactive design tool that would invite city stakeholders, designers, developers, and policymakers alike to consider the impacts of our decisions at the most granular level. In visualizing different futures of our city, we can ask ourselves which trajectory aligns most with an urban fabric that is more equitable, resilient, sustainable, and healthy, and how do we challenge and reorganize the forces that shape our city to arrive at that desired outcome. And as we mentioned before, this project is fundamentally about process and what machine learning can unlock for designers. And we can imagine its application in our studios to not only predict trajectories of development, as you see here, but it could also be leveraged as a tool to advance some of the other research you've seen today, such as the California wildfire research that Justin and Dan presented. And with that, I think that's the last of our research. Thank you.
Thank you very much, everyone, for presenting. That was great. And I'm just going to ask everybody to turn their cameras on for the panel discussion. For our guests, if you could please post any questions in the Q&A box. We are scheduled to end at 1:30. And what I've asked the panel is that this is not just a one-way discussion with me asking questions, but a discussion among everybody here. Because a lot has been presented as some very interesting things. And I just wanted to kick off with a couple of questions about what Neil talked about. When you were talking about tool development, I was wondering how that relates, like when SOM is developing a tool, how that relates to like a goal that that you're trying to achieve, or does the tool precede the achievement of the goal? So I guess that's one of my questions. And then you also mentioned the difference between computational thinking and kind of traditional design. And I was going to ask how you think about that.
Okay, so the development of tools, we've done both. Usually a tool is in response to a project need. Someone wants to do something and either they're unable to, or the method that they consider using is very tedious. So they'll often come to someone in our group and say, can you help me do this? And we'll develop a tool that they can use to make their process more efficient. Sometimes we'll develop tools because we think that might be useful, and then try them out with teams. That doesn't happen as often, but we've done that as well. In terms of computational design thinking, as opposed to maybe a more traditional design method, I typically define computational design not necessarily using computers to do design, although I think it's an invaluable tool in this type of thinking. But I think it's the type of thinking that really defines it for me. And it's thinking in a logical and geometric or mathematical way. It's applying some rigor in how we develop designs for projects.
I wanted to talk a little bit about the spatial laminated timber that Kyle and Benton talked about. And I just wanted to ask if you could describe the process of the collaboration with the community to do that, because that was one of the goals, I think, of this biennial, to activate different empty lots, sometimes in really disadvantaged communities, and to try to work with the community. And I'm wondering how that process went.
Yeah, it was actually quite simple. The principal or the director, Leong Khan, asked us for a space to create a space outdoors, and it had to fit into a certain place, in the parking lot of the school. And there were a few other criteria, but for the most part, it was just about creating a space outdoors. Since then, it's been kind of exciting to see how the students respond to it. There's been a lot of tracking of the sun through the lattice work of the timber elements. In fact, I think the students have been with chalk tracking how the sun path has adjusted over the course of the fall here into the winter. And it's been used for, I think, a lot of other. It's being used in a lot more ways than we expected. We initially expected a class or two to be held each day there, but it's really been its use has been shifted more towards collaborative events with the community. Like I said, with Chicago State in particular, they've held a few workshops. We had a concert with Thaddeus Tukes, who was a local jazz artist, which again was open to the community. So I think the big story to tell with the kind of local collaboration is just creating connections between other folks in the community and Epic Academy.
And do you feel like you achieved like some of the goals that you wanted to achieve with the project as far as like community integration or community participation?
I think so. I mean, it's a pretty light touch, right? We're not building another school or anything like that. You know, it's simply just an outdoor space. And so I you know, we didn't have, you know, our expectations weren't too high. Again, we just wanted to create a space outdoors for students to learn in. But I think, yeah, I think it's been exciting, and Leong Khan has had a lot of really nice things to say about what it's done for the pedagogy of the school. So.
Feel free, anybody, to jump in. I know originally we talked about whether I was going to moderate this or whether it was going to be a discussion. So I'm inviting everybody to jump into the discussion. So about the 3D printed components and also the Moon Village, I'm wondering, was there a relationship between these two projects, or was this like kind of two separate strands of research that came together at the Biennial or at the Venice Biennale?
No, one definitely came out of the other. You know, we had this ongoing relationship with the European Space Agency and the research that Daniel explained, and when our relationship with the Venice Biennale was a separate thing that came about, and those two came together. And then we wanted to explore, not just to, you know, build a mock-up of our Moon Village design, but to use the opportunity to explore new ways of building as well. And it not only those two, but the whole idea that throughout SOM, with all this other research, the idea of 3D printing and exploring what these new digital fabrication techniques could be, and to help out. So it's kind of multiple connections coming together to that.
So do you view like that kind of research as then something that's integrated into bigger projects? Like is the research and kind of a test case for bigger projects, or?
Maybe I can speak to that. Is that okay? So I was thinking that question is interesting because if you think about research, you know, research in either case, you're trying to apply it to, you know, practical scenarios. And I think one of the key aspects of at least this work with ESA and other entities in aerospace is that the space and aerospace sectors, they approach design and engineering problems very differently because they have to perform under different environments and they work with different technologies, you know, very complex technologies. So when you start to think about those kinds of integrations, immediately you start to look for opportunities to take that thinking and that knowledge and apply it to the building sector. And so some of that research has definitely, I think, caught our attention. It's not just in manufacturing, but also in thinking about how we develop, you know, processes from digital modeling, you know, extracting metrics, extracting data from our models, not just thinking about design as something that's, producing an aesthetic quality, but producing information that can be shared across disciplines. And then at the same time, thinking about how do you bring new knowledge from industries that are being developed right now into the practice of building design, because material technologies, you know, they're for the most part, the building industry is using a lot of, you know, very old materials, but more and more new materials are coming into existence that we can start to think about using, and that, you know, that crosses the bridge between things from the, you know, biological sphere to the more, you know, kind of like natural materials that we're used to, like stones and concretes. So I think there's definitely a lot of opportunity. Like one example I'll give you is we were designing a tower in Asia where we started thinking about BIPVs, and you know, BIPVs are very interesting for facade applications, and it's difficult for any designer to immediately understand how much energy can you get from a BIPV on a facade if you're covering it with 40%. But if you know that the highest performing BIPV is somewhere around, you know, 15 to 17%, you can start to look at the space sector and say, hey, these, you know, there's 30% efficiency PVs being developed in the space sector. Imagine in the future if you design your building so that you can swap out the BIPV with a higher performing one in the future. So I think of the architecture as a vehicle for applying new material technologies that could generate power, that can produce food, those kinds of things that are being explored in other sectors. So, I mean, that's just one example of how I think we have used the research to apply more rigor to the way that we design.
So just for the sake of our audience who may not understand what BIPV means, can you please define that?
Sure, building integrated photovoltaic systems. So they're thin cell technologies that are applied, as a laminate. You can apply it to a glass or a substrate, and then you can either allow it to be translucent, or you can see through it. You can allow light to come through it, or you can apply it directly to something that's opaque. Yeah.
Thank you. For anybody that wants to jump into this conversation, I think it would be nice if we could have a cross conversation.
I have a comment maybe that I can share and people can address it. You asked about a traditional design process, which I think involves a lot of intuition. And I think a lot of the research that we're doing in all aspects and at all scales sort of defies intuition. Things like some of the structural analysis, which might suggest structural systems that we otherwise wouldn't have thought of, or things like machine learning that might show us things that we wouldn't otherwise see. So I think a lot of this research and a lot of the innovation that we're developing through the research is causing us to rethink intuition or to change our intuition.
Yeah, I guess the question about that is, do you think as you develop specific tools and processes, you kind of start to develop a new level of intuition that has to do with, those tools and processes?
I say absolutely. And I'm interested in others' responses to that. I mean, my intuition has definitely changed. Looking at some of the structural analysis, right? You look at a structure or a building that you need to apply a structure to, and you have ideas about what it might look like. But then some of the analysis shows that, it could be very different and more efficient.
Kind of like thinking about intuition as a record of, your experience. So when you make decisions as you get more experience, your intuition gets better and better. But with new technologies where you get a lot of information very quickly and you're thinking, through design problems, mathematically, even though you don't realize it, you're thinking through them through computation, you're getting a lot of feedback immediately that allows you to make better decisions without actually having to build up all that experience. So you can almost like bridge the gap between, being an early, thinker, like a designer who's just, thinking in the clouds versus someone who has a lot of experience engineering and solving problems. And I think that's what technology allows us to do, is to bridge that gap and just be more creative. And I don't know if you guys feel the same way, but
yeah, no, it's an interesting point, because like when we do like machine learning and stuff like that, you're really training the machine's intuition, I'll say, right? You're showing them a bunch of examples and it's getting smarter and smarter at being able to recognize those things. And it is quite interesting, as Neil has mentioned, about some of these kind of, structural analysis images that come out and things like that. It really does kind of rewire your brain in terms of like seeing load flows and how they curve, towards supports or how they try to move and blend through. And so it is sort of an interesting take on the whole thing, because once you've understood kind of how these things operate, just watching them take on a new life of their own as you approach and try to apply it in other situations, non-building structures and different devices and things like that. And it just becomes this, I'll say, reinforced behavior that happens. It's like the cyclical reinforced behavior that ends up creating, new avenues for research through that intuition.
And I just add to that too, thinking back to one of the first design reviews that the research team presented, this speculative question for the machine learning urban development predictor to a larger group of designers at SOM. The question and challenge was sort of posed to us, well, is this model just going to validate what we already know about the city, or is it going to spit back, patterns and trajectories of the city that we would already anticipate with the body of knowledge that we have, and being specialists in design, And in some ways, as you saw in the research, it did validate some of those conclusions. But I think the conversation about resolution and fidelity is really interesting too, that you can dive in even further and start to understand, like with Georgie's talking about, 3 millimeter lamination on the 3D printing, all the way to talking about a singular property in machine learning. Being able to approach that resolution with data, I think, is invaluable, even if it does parallel some of the things we would assume to see going on, whether it be in a city, a building, or whatever scale.
Yeah, I think that I asked a question when I first met with you guys, and I saw Stephanie and Grant's presentation about like how you train that model and what kind of results you get based on that. So I guess the question is how do you iterate, or how do you kind of how does the designer come into the process, I guess? As you're discovering solutions, how exactly do you start making decisions about what else to feed into the system, or what to take out, or where to intervene? Because you said there's definitely an intervention that was done at the end.
Yeah, we were talking about this just recently too, that there were sort of two bookends to that sort of intervention. There's at the end of our presentation where we showed those sort of theoretical futures, if we were to sort of manually manipulate these weights and see how the trajectory of development in San Francisco could change. That's certainly one type of intervention. Another very common type of intervention in machine learning at an urban scale is the sort of gamification of machine learning, and another type of machine learning called reinforcement learning, where you're training a machine with reward and consequence to develop things in a certain way. The other type of intervention that I think is less clear but just equally important is the intervention at the beginning of the research, where you are curating data, you are sourcing and unveiling a design question. And honestly, a huge chunk of the research time was spent in developing just the approach to the machine learning model alone, being able to sift together this open, inclusive collection of data and to make sure that it was calibrated to a question we could actually ask. There were many other different types of applicable machine learning scenarios that we were interested in that we strictly couldn't proceed with because the available data to answer that question in a meaningful way wasn't available. And so there's certainly on the other side of the research, the opportunity for us to intervene and to kind of help shape those forces and to think about maybe zoning at a more granular level. And I think a lot of it needs to still be done in this sort of, specifically with the machine learning research, this sort of supervised machine learning approach where it unveils the patterns, right? And maybe that opens up the doors for us to take that knowledge, discern what those patterns are, and then maybe take the next step to a reinforcement learning model or something where we actually try to approach maybe an algorithmic zoning, like a hypothetical scenario or something like that.
So I want to touch on Luke's presentation and also Justin and Daniel's presentation, because those were very environmentally focused. And I just wanted you guys to talk a little bit about the initiatives that SOM has towards sustainable design. And also, I mean, I consider the wildfires a big sustainability question as well. So I was wondering if you guys can talk about that a little bit.
Sure. I'm going to have to keep my camera off because I don't think you want to see what I'm looking at right now. But having said that, yes, we do have what SOM focus on right now is by the year 2040. We believe it's important to keep the world at 1.5 degrees C compared to pre-industrial revolution temperature to make sure this climate change is not going to impact us. As you know, it is code red for humanity according to IPCC. But I think it's the longer run, it's beyond the carbon issue, it's the human health. Earlier, Benton mentioned through some of this exercise, we rewire our brains. Well, you know what? We don't even know how our brain wired to start with. So through some of this research, we are really focused back on what exactly do we mean by human-centric design? Do we understand human beings? And the more we look at it, we find out aspects that we do not know before. Because at the end of the day, we design the environment, and the environment in turn shapes us. So it's very important to know what we are doing. And chances are we probably have room to grow to understand what exactly does it mean when we say designing a human habitat.
And I think you're totally right in terms of climate change and wildfires. They're so linked together. As we mentioned, climate change is one of the leading drivers of wildfires and causing more wildfires every year. But then you can even think of all the emissions from a single wildfire probably are a lot more than what we're trying to conserve by designing our buildings a certain way. So it makes you think about how we can have bigger impacts, which definitely.
And just to add to that, I think, this isn't just about the California issue. I think,
right.
This is a sustainability, related issue for, the whole, really the planet, but really, we're thinking beyond California. I think this is probably the first step in doing so. I think it's about thinking about what's happening across in Canada, for example. They're having the similar issue with wildfire, and different regions in the U.S. is having the same issue with wildfire. So I think for us, sustainability, yes, is in the first kind of the question that we are thinking about, but it's also not limiting ourselves to just California. It's about thinking about how this could be applicable in many different regions around the world.
Yeah, definitely. And I think this is a great example of SOM's research on how we're taking something that we want to focus on, that we all know is important, that we can have a big impact on the world and the built world. Even if it's not something that necessarily a client is coming to us and saying, hey, we need you to design a building. All of the presentations we talked on today are something that we think is important that needs to be done, that is outside of kind of that client-driven design.
I guess sorry, go ahead.
I was going to add a little bit on maybe a little bit more narrow addition to this. We talked quite a bit, and we saw a couple of examples in the presentations of the collaboration between the structures and the digital design in coming up with shapes that you wouldn't expect intuitively, right? This thing about the intuition that are much more efficient material-wise, but I don't think we showed any, and I want to highlight that we do have quite a few tools that is a collaboration between the digital design and the sustainability group in how to shape buildings super efficiently from a energy point of view and from a daylighting point of view. So I don't know, Neil and Luke, you guys are the leaders in that, but I want to point out that there's a whole field of tools that we have for that type of optimization from a sustainability point of view.
Also in the urban scale as well, glad that you mentioned it, because collaboration between city planning and urban design at SOM with Luke and his group with sustainability, we rely on them heavily to actually guide us for many projects. So it's definitely something that's a part of our working flow.
So I guess a question I have that relates to something that David Brown said, who's the artistic director of the Biennial this year, about kind of creating a more collaborative, transparent design process that probably has to do with larger urban design issues. And I guess my question is there an opportunity for the computational tools that you guys were developing and the processes and all the design expertise to kind of develop something that starts to look maybe closer at zoning, let's say. So I'm seeing that in the machine learning project that you guys did, but I'm wondering if you're also starting to apply it to like, petitioning for policy changes and stuff like that.
Well, I guess I could say, we see that as an inevitable next step with speaking specifically about the research we presented today with the machine learning, that, and I think it's similar to the ambition with the wildfire research, right, is that whether it is a set of proposals of guidelines or it's a tool that helps us better understand the patterns of the city, that a lot of these research initiatives end with us being able to engage with other people. And in this case, this would not just be an insular tool at SOM for us to understand how the city is changing. It would be an opportunity for us to engage policymakers and city planners to understand, how we want to shape the city. Because once again, the research that we presented looks at the historic trends of development. And that's what trains the model to understand what the trajectory is if we don't intervene and change. And to your point about zoning, we also saw that the machine learning model, as we would suspect, overwhelmingly gave importance and weight to zoning and use in terms of classifying susceptibility and where properties would change. And so I think the promise of being able to engage policymakers to, challenge how we approach zoning, to think of it at a very granular level, to sort of think of it, at whatever scale we want to approach it in. But, I think these tools can challenge those sort of broader strokes with which we typically paint the city.
So I see that we have a question here from a guest, and it says, thanks everyone, very refreshing thinking. My question concerns the notion of social innovation, a concept which is taking hold in cities and city management to refocus concerns on people and channel resources more safely. How do your studies, data collection maybe address social innovation?
I guess I can touch on that really quickly, since we were talking about the machine learning research. I think specifically the data collection and what informs some of this predictive modeling was a really interesting question for us. And you saw a little bit of a preview in that hypothetical last slide where we were manually shifting weights. What if we were to completely ignore zoning whatsoever in the original weights of the machine learning model and just amp up to 11 proximity to parks and public bikeways and things like that? And I think that's where this notion of gamification and creating rewarding urban environments with predictive modeling is really interesting. How can you, through the data that you curate, encourage development that makes access to amenities like parks and public transportation more equitable for people, right? Like, how do you distribute density? How do you maximize multimodal transportation? And I think collecting the right data to answer those questions is a critical first step, at least in the scale of the city.
Maybe that's another place where designers can have a bigger impact as well, because I think an SOM has lots of equity committees outside of the ones you've seen today that are looking at social issues separate from research. But I think designers probably can have an impact there, where some of the data has been biased by years and years of let's say, unfair practices. And so we can, as designers, kind of bend that data a little to try to be more societally fair and socially fair.
Yeah, this is Luke here. Regarding the zoning question, around the nation right now, from Boston to New York, there's zoning requirement on your carbon, and it is punitive. So one of the tools we are developing is this whole life carbon tool we call EC101 to apply to our projects. So when we do these projects in the future to minimize the carbon production. And also on the equity side, we've been collecting air quality data in different parts of the world. And we should make, in the future, our urban environment, people has clean air to breathe. Right now, it is not the case. Majority of the bad air area is actually in the poor area where people are not as privileged. So yes, I think through those data, we can change the world to a greener and a more equitable future.
So what to that point, Luke, I think one of the questions is maybe one of the problems with the zoning is that as populations shifted around, like to areas that were perhaps industrial before, and there's never been kind of a rezoning effort or anything like that. some strange adjacencies start to happen that influence health issues, but also other design issues. And I'm wondering how you guys view that, because I know there's nobody here from the urban planning group, at least I don't think so. But I'm wondering how you guys interface with those problems.
Well, I can go first. The topic here is we need, by the way, United Nations World Health Organization just come out with a new standard. Having clean air to breathe, clean water for people to drink. This is not a luxury as portrayed in Wall Street Journal a few months ago. It is an equity issue and basically a human right. So if we do look at zoning issues like that, and there's an environmental problem, first, obviously, you try to fix the root cause of it. But if there's something that you cannot fix, there are measures we can do indoor to make it more equitable for those buildings to have clean air to breathe and clean water to drink. So yes, those are important issues to look at.
Do you feel like those are those architectural issues, are those design issues, or, I mean, I remember, you know, when I was at SOM and we were working on, you know, green buildings and looking at sort of forming buildings in a way that you guys just talked about a few minutes ago, forming them so that they are, you know, exchanging with the environment in a certain way. But I'm wondering if these larger issues, how do designers and urban planners actually interface with those issues, or are those more issues for politicians, for scientists? I'm just wondering what our role is in that, you know, beyond kind of exercising a green design to the best of our ability.
Maybe I can speak to that a little, only because I've recently been working on a very large urban plan project. And from a design perspective, you know, we've been working with urban designers across offices, and the urban designers, they really set kind of the tone for how the architecture starts to take place. And from this exercise, it really starts from a standpoint of mobility and density, thinking about how dense you want certain parts of a city to be, the kinds of amenities that you want within that city, and then how do you get to those destination points? Because as soon as you create a sense of civic space, that's where value typically starts to accumulate, and that value increases the density. And so there's new modes of transportation, you know, typically the car, which produces a lot of CO2. It also generates, you know, a lot of encumbrances for people to move around the city. But in the future, there's different types of mobility that could start to take place, things like autonomous vehicles underground, you know, railway stations, or things like the Hyperloop. And so thinking about these, or integrating these kinds of mobility strategies into future urban scenarios really helps us recreate the architecture. And for instance, you know, building typologies, especially in dense cities, they can start to take on new forms. You know, you can imagine buildings where it's not just a facade treatment. Greenery is not just a facade treatment, but it becomes part of, you know, the kind of like the oxygen replenishment system, where things are being integrated into the building that can help you not just have exposure to nature, which is actually very important, but also contribute to the resources needed within the city, whether it's oxygen or, you know, ventilation or power. And so the building forms can start to take shape around that. I mean, even thinking about like large tower skyscrapers, when you get to a certain height, you can start to think differently about the form and shape of a building, because it traverses so many, you know, kind of like different areas of the environment that you can take the hot air, you can move it through the building, you can start to provide cleaner oxygen to the occupants. And I think that really provides a new approach to designing new urban infrastructure. So yeah, just some thoughts on this, because I think it's important for us to think about, you know, building design as integrated into the urban scenarios.
And because of the
I guess
scale of the
my-
projects that we do, we have an opportunity to have an influence there. So not just designing buildings within an existing urban environment, but designing cities and taking, buildings' relationships to each other into account, and green spaces and mobility, walkability, all kinds of things like that.
So I guess my question about that, though, is about timescales. So, urban planning typically is, you can have a plan that projects the next 50 years. And a lot of times there are failures over time because of that, because the projection is such long term. And so I guess the question is, how can we interface with those timescales? Does, that kind of central planning really still work? Do we have just, like the granular project that you guys discussed, looking at how data informs city planning? What are some of the timescales that we should be planning in, or how can we kind of loosen up the timescales so that the city can transform faster as needed?
Well, I might.
Oh, sorry.
Sorry, go ahead, Justin.
No, I just want to say, I think there are probably minimum two factors, I think, dealing with, the length of the time required for an urban design or planning, projects to actually come to fruition. And I think one is, data that we've spoke about before, but then also the other is just ecology in general. I think to us, every cities that we design and, is we are actually responding to not just the immediate adjacent, environment, but we're really thinking about the larger ecological system that we're going to be working in. So to us, I think being able to create something that's smart in terms of its design, that is, driven after data and research, but also always responding to nature, so that in the long run, we're creating a very smart, kind of a flexible, city that can be adaptable over time. So yes, if it does take 50 years to build, we want to have a design that is responding to, the data and the resource that's kind of the current, but at the same time looking at it in a longer trajectory. And to us, I think, to me at least, that is always going to be the ecology and the nature that we're always going to be responding to. So, 50 years, yeah, it's a long time, but in some ways, thinking about it in the ecological term, I think it's minuscule, I think. So I think in some ways, I think a lot of the projects that we work on at SOM, not just a city scale, but all scales that is involved in any project is responding to data and nature in mind.
So I guess with that comes the question of like, this was discussed a lot in some of the earlier sessions that we had, like this idea that architecture is a form of social communication, and that the quality of spaces, can create or reinforce certain opportunities for, social interaction. Not just social interaction, but also business interaction. And I'm just wondering if anybody here can talk about how you guys approach this, because I think that would be really interesting for the audience to hear. Because so far we've talked about a lot of technical issues that kind of inform design decisions, which is extremely important, but also kind of the idea that architecture is also a formal language, and how that also helps, societally.
I would just say that
Question.
Open space, so public space, has to be rethought, because a lot of commercial space, private space, that's something that is it's limited with how many people can interact sometimes. So creating a real sense of public and civic space where people can bring unplanned activities to the city, to the urban scale. And I think parks, making sure that we have enough park space, looking at what is a percentage of park and open space to a certain part of the city, just finding ways to create amenities around those open spaces so that they can become comfortable for the pedestrians and the local inhabitants. So there's some of these things are really like product design sometimes, and even technology designs, thinking about ways of talking to the right people who can introduce new systems into the urban scale. So I mean, at least from my experience, when you go into a city, if you have enough amenities within a public space, you make use of that space. And I think that's something that architects have to start to envision in the way that we imagine urban spaces. Markets, for example, they don't have to be formal markets. They could be informal markets. Places for recreation, they don't have to be formal. They can be informal. So I think there's a lot we can learn from, things like historic cities, emergent cities, where things happen informally. And maybe that's something that we have to get into the habit of making room for that kind of space to take place.
Yeah, I think, so that's super important. I think the more we, the more we focus on the relationship between data and livability and the quality of the urban realm, we think more about urban design. I think we're all, even as architects, excited about urban design. I think another part of this that I think permeates through most of the projects discussed here today is kind of the almost like character or heterogeneity of the built environment. I think, over the last 50 to 100 years, right, we've gone through rapid industrialization, and Taylorist manufacturing processes have come to define our cities. And I think just anecdotally, we all still kind of have a love for the medieval city, or the old colonial city, because it has a scale that's more related to ourselves, right? But we've sort of sacrificed some of this for efficiency and for scale, right, and for density. And what is exciting about a lot of the technologies that are being discussed today is that they offer a lot of new opportunities for new modes of craft and construction, which is more, we'll say, expressive in any way that you want to say, whether it be in terms of its expression of culture, character, place, technology, like all of these things, I think will become more prominent again in our built environment. And cities will hopefully become more responsive, right? And we'll find ways to solve some of the scalar problems that we've created for ourselves over the last, again, 50 to 100 years. So I think we're entering a really exciting era for architecture and engineering, because we're sort of opening up the material palette. Whereas I think, again, we've kind of consigned ourselves to steel and concrete and glass, and I think it's exciting to think of ourselves as being more crafty moving forward.
Can I take a stab also at this question? I think something that we've discussed and touched upon and keeps getting talked about is that the big challenge for humanity in the next 50 years is the climate change. And we in the construction industry in making the built environment have a big chunk of what's causing it, right? The way the buildings are built and operated is a large chunk of the release of carbon in the atmosphere. And that's all taking place while the human population is about to projected to increase by 2 to 3 more billion people in the next 25 years. Depends on how you do projections. And so when you think about it, us as architects, and especially the younger generation coming in the next 25 years, we're going to have to make buildings for another 3 billion people to live in and work in and do everything that humans do, right? We're going to need a lot more buildings. And how we construct these buildings in the next 25 years is going to have a gigantic impact on how humans live on the planet. And so I think that's the biggest societal impact that we can have as designers. And we're trying our best here to come up with solutions and ideas of how to build better so that this legacy of climate change from the past 50 years is not what happens in the next 25.
Yeah, I mean, I completely agree, but I'm wondering, SOM always practices like the gold standard of I don't mean gold lead, but I mean like the gold standard of sustainability. And I think most big architecture firms do. And I think it's also a question of cost. But I'm wondering, you know, for like just looking at it from a design perspective, because I think technically it's possible to achieve very high sustainability, but how that then really transforms design as sort of social functionality of design and how those two things are related. And so I know, like, for instance, the towers that SOM designs, you know, necessarily have to be very focused on the structure. I mean, there's a lot of structural innovation in those towers. And there has to be, absolutely. And sometimes, you know, an architectural design can't really drive that process. But now, because we have tools that can integrate those two processes, and I know like architects can use tools at the front end that are sort of common to a structures group and a design group, and can kind of co-design that. I wonder like how the design initiatives that you guys are doing are also responding to, you know, questions of how such a much higher density of people will be living together. It's kind of a broad question and maybe hard to answer, but I think I'm just asking a question about the relationship between sort of the design and all the structural necessities and then all the social necessities that have to do with living in a higher density.
I mean,
Well, I think
one way is that I don't know if we're leading that, but we're running out of places to build in the cities, and so seems like every construction project we've been involved in recently is involved building under not the ultimate place. You know, very often in dense cities, the last bits of places to build is over train tracks and infrastructure. There's actually a great synergy there because usually that train infrastructure is where all the people are commuting in by train. And so by placing these large new developments over this land, it's very challenging design-wise, architectural-wise, and structure-wise, but it's really key to put these big buildings, put the density to where the people are so they could get to these places, you know, with mass transit and things like that. So that's one way we're addressing that.
And those kinds of constraints usually lead to innovations in structural design.
Well, I think one constraint that is, you know, particularly compelling is the fact that like we don't need super high density, right? We need a medium level of density. I think the UN panel on climate change suggests something like 13 to 17 stories or something like that, to kind of balance, you know, carbon intensity with the, you know, the urbanization and density that we'll see over the next 50 years, right? So, you know, how do you optimize for that? You know, often we're looking at how do you optimize for a much taller height, right? But how do you optimize for that region? I think it's also interesting, and Ben, correct me if I'm wrong, but this is kind of where we're peaking out right now with timber, right? Which may be a happy place to peak out.
Yeah, no, it's a good point. Like what is appropriate in terms of the development and what is that upfront carbon investment? I think one thing that people, you know, don't think about as often is that carbon that's released with the initial building construction is trapped up in the atmosphere for a longer period of time. So there's actually like a time intensity issue that needs to be dealt with as well. Like carbon spent now is far more expensive than carbon spent in the future in terms of its cascading effects. And so, you know, I think that's a really big part of the research is not trying to just push limits for limits' sake, but trying to identify like where we can be as targeted as possible with our efforts.
And I think a lot of this is kind of tying back to what you touched on earlier, is that, yes, we're architects, we're thinking about these things, But we're just one architecture firm, and even if we're doing some big buildings, one big building making, LEED Platinum is not going to make the difference that needs to be done. And so a lot of these tools and discussions that we're having are trying to inform policies and trying to inform politicians, trying to inform the industry and push the industry to make an impact that can go beyond SOM.
Into Georgie's point, transit-oriented development, has definitely defined our cities again for the last 100 years. But what happens when we get into more decentralized networks? If the promise of that comes true, right, and the last mile is kind of distributed throughout the city, and everyone is using autonomous vehicles as public transport, does that change the way we think about density, and does it change the way we think about access? It probably does if we can actually get there. And I know, Daniela, that this has been, a topic of these debates. So it's almost like too abstract to even speculate as to where it's going, but also kind of imminent in a way. So.
Well, I mean, the first two sessions were focused on, the blockchain metaverse. I mean, the metaverse is kind of a new concept of not just integrating technologies, but spatially integrating the internet so that we can have interaction in a certain way. So that there can be, for instance, a process by which, digital twins of a city develop, are an outcome of a process of architects working together in one space, which we don't typically do, right? I mean, typically each office kind of has its virtual environments, or there are virtual environments that are pre-built that can be interacted with, but not necessarily like a space where something can be developed that later can be actualized or partially actualized. But beyond that, we're talking about blockchain, which is, mystifying to a lot of people. I mean, people think of it as associated with cryptocurrency, but it's really the technology that's very interesting. What can you do with a distributed open ledger that records, let's say, every building component? Or, how can you activate sort of a social process, for voting on the built environment, let's say. So that's how we were discussing distributed systems, really. And that kind of relates to the theme of the biennial, in that a distributed system is capable of responding to people maybe perhaps faster or more spontaneously as well. Like there's possibility for more communication that takes place in a ledger that everybody can see. So that's the way that we were discussing about sort of distributed systems. But the idea wasn't, to create something that stays online, but to think about the integration of like an online space or community into sort of a cyber physical environment or a physical environment. So one of the things you guys said you wanted to talk about was like the future workspace, for instance. And we were talking a lot about like how that needs to take place online largely still, and how that's going to be impacting how buildings are built in the future. So I'm wondering if you guys want to talk about that at all. Maybe not.
I can maybe touch on that. I was working on a project recently where part of the requirement was to introduce a public space at the ground level. And so we had a certain, area that had to be part of the project. But then on top of that, we started thinking, how can we take that public space and not just make it accessible at the street level, but start to introduce, public gardens throughout the tower. But one of the challenges is that how do you make use of those spaces? When you have all these office workspaces happening in between, how do you share that space? And I think that's one of the key things about, generating resources like fresh oxygen or just a sense of well-being. So that's one of the key attributes of having public spaces or sharing natural spaces within large towers, or even lower, mid-rise towers. And I think that has to do with, not just thinking about natural ventilation, thermal comfort, daylighting, thermal performance, but simulating that and trying to validate that the way that you're thinking about introducing these spaces actually is performing the way that you imagine it. And that's part of what the tools allow us to do, is to think about, these architectural ideas for the occupants, but also to validate and look at the information of how those spaces are actually being activated within the building, or even at an urban scale. Thinking about you doing computational analysis at the urban scale is also something very meaningful, because it helps us shape buildings in a certain way. And there's a certain kind of, I think, like push and pull between, different buildings, where you have to have a certain scale adjacent to another building, and a certain kind of material application, a certain kind of, like orientation to really respond at the urban scale. If a city behaved that way, I think it would be more, in line with what you're thinking about, like distributed system. Like, how can buildings speak to each other? How can they really interact with each other, and not just have the same rule set for every single building, but have them be a little bit more concurrent in the way that they're being developed. And the other thing I think was interesting is that it's not just about building new buildings for the future population, but also rethinking how we retrofit buildings. In New York, especially, there's so much building stock, and the challenge is looking for new places to build new ideas. But what about the buildings that exist? There's so many potentially usable buildings. You can retrofit them, you can reimagine their function, and you can make them part of the urban environment in a more meaningful way. So I think there's that opportunity as well, and we do that as well. SOM has worked on that kind of work as well. Yeah.
So we are at 1:30 right now, which was the scheduled time to end. And since we don't have any new questions, I'm just going to ask if anybody wants to leave us with some parting thoughts, like something you want to convey before we wrap up.
Well, I'll say that Splam is open to the public. It's in the South Shore community as we speak at Epic Academy. So please go visit it if you have a chance and you're in Chicago.
Thank you. Okay, so I just want to thank everybody for being here and for agreeing to do this. It's been a really great session. And with that, I'm going to close. And for anybody that's here that's interested in the upcoming sessions, please visit the Chicago Architecture Biennial calendar for this month, and you can register for the events for free. So thank you, everyone.
Yeah.
Thank you.
Take care.
Thank you.